So, as promised, I'm gonna redo this video just because I think the background noise for my first video on this was pretty atrocious. And I really do apologize for that. I just didn't have any quiet space to get this done. So let's run through 7.3 with some more clear audio. And make my video a little bigger so you can see me more. All right, so what are our learning objectives here? We are going to find function values for our sine and cosine, our famous angles 30, 45, 60, which is pi over 6, pi over 4, and pi over 3 in terms of radians. Our second objective, we're going to identify our domain and range of our sine and cosine functions. Our third one, the most important, find our reference angles and identify what reference angles are. And then our fourth, we are going to use our reference angles to evaluate trig functions. So some vocabulary words. Unit circle, which you are quite familiar with at this point in time. Our unit circle always centers at the origin 0, 0 and has a radius of 1. And what we are going to learn from a trigonometric perspective is the fact that any point on the circle, our x comma y, from a polar coordinates form is just cosine t comma sine t. So this is a famous conversion that we'll be practicing a lot during this section. Our sine function of an angle t represents the y value, whereas our cosine function of an angle t represents the x, aka x is cosine t, y is sine t. And I'll color coordinate for you guys. We'll make our x and cosine t yellow and our y and sine t purple. I think there was, yeah, cosine is just 1s. So now we're at our first example where we want to just simply find our cosine t and our sine t. Again, cosine t is just our x value, which is 1/2 here. And then our sine t is our purple, which is square root of 3 over 2. And we're done. Maybe I'll use a different pen, change it to black. Much better. Example 2, we're now being asked the same type of question, but we're not given the graph. We are given just a coordinate. So it's a little bit more technical, but as long as you apply the rules, then it's very straightforward. Yellow is yellow, purple is purple. So our final result, or results, cosine t is equal to negative square root of 2 over 2, and sine of t is equal to positive square root of 2 over 2. Finding sines and cosines of angles on an axis, also known as quadrantal. I don't know if I'm pronouncing that correctly. Quadrantal angles. Quadrantal angles? I think it's quadrantal angles. But these are just angles that fall on your x or your y-axis. So an example, 90 degrees, which, would you look at that? We arrive at example 3. How do we find cosine of 90? How do we find sine of 90? Well, let's look at this graphically. 90 hits along our y-axis. And if we're looking at a unit circle, what is the coordinate at this point? This is just 0, 1. Well, 0, 1, this is our x, y. This is our cosine of t, sine of t. T being 90 degrees. So cosine of t is 0, which is cosine of 90. And sine of t is 1, sine of 90. There we have it. Pythagorean identity. Our famous Pythagorean identity is our sine squared theta plus cosine squared theta equals 1. They put the cosine squared first, but addition is commutative, so it's interchangeable. And again, if we look at this from our right triangle perspective, what's our Pythagorean theorem? A squared plus b squared equals c squared, which in this case are x squared plus our y squared, dealing with the unit circle, radius of 1 equals 1 squared, which is 1. X squared plus y squared equals 1. And then if we want to convert it into our polar coordinates, our cosine t comma sine t, we plug that in and we get our Pythagorean identity, cosine squared t plus sine squared t is equal to 1. So now let's apply it to this problem. If we want to find cosine t and we're given that sine t is equal to 3 over 7, well, sine squared t plus cosine squared t equals 1. 3/7 squared plus cosine squared t equals 1. 9 over 49 plus cosine squared t equals, let's say 1 is the same as 49 over 49. Why did we do that? Well, because now we're going to subtract 9 over 49 from both sides, and when we do, it'll be very easy to simplify that right-hand side since the denominators are already the same. That just becomes 40 over 49. Now let's take the square root of both sides. Square root of 40 can be broken up into the square root of 4, square root of 10. Square root of 49 is 7. And so this just simply reduces to 2 square root of 10 over 7, which is your answer. Another way you can go about doing this is you can create a right triangle. You know from your acronym SOHCAHTOA, your sine is equal to your opposite over your hypotenuse, so 3 over 7. And then by Pythagorean theorem, you can solve for our x. 3 squared plus x squared equals 7 squared. X squared equals 49 minus 9. And then x is equal to the square root of 40, which is simply 2 square root of 10. And so if x is 2 square root of 10, what is our cosine of t? Cosine Ka is our adjacent side over our hypotenuse, which is 2 square root of 10 over 7. And that's exactly what we got down below. So either method works in getting your final result. This slide is just highlighting our sines and cosines dealing with our 45, 45, 90-degree triangles. So what is cosine of 45? And then what is our sine of 45? We look at the proportionalities of the sides, which we'll get into very, very soon. And then the next slide is more when we're looking at it now from our 30, 60, 90-degree triangles. Again, proportionality of sides. And we'll do some practice with that very soon. So, all in all, what have we covered here? We know our sine and cosine of our famous 0, 30, 45, 60, and 90-degree angles. And I'm actually going to create a slide here on teaching you guys a trick in how to memorize all of these angles quite efficiently. I'm only going to put in our sine, cosine, and tangent, and that's because when we look at our cosecant, secant, and cotangent, you can just take the reciprocal. I should have put in maybe one more. You know what I'll do? I'll just draw a little line at the top. Okay, so our thetas, 0, 30, 45, 60, 90. We're looking at sine of theta, cosine of theta, and our tangent of theta. 0 degrees is the same as 0 radians. 30 degrees is the same as pi over 6 radians. 45 degrees is the same as pi over 4 radians. 60 degrees is the same as pi over 3 radians, and then 90 degrees is the same as pi over 2 radians. Now, the next thing that you need to know is our special key. And our special key is what helps us fill out this whole table. It's simply the square root of n over 4, which is the same as the square root of n over the square root of 4, or you can just remember it as the square root of n over 2. But it's important to know that your n value starts at 0 and then goes up incrementally by 1 up until 4. So n is an element of, we can either say the whole number, 0, 1, 2, 3, 4. You can state it as, these are a few different ways to state it, the natural numbers, but including 0, or you can just say n is equal to the set 0, 1, 2, 3, and 4. I think the last one is probably the most accurate. But the important thing is really just remembering that square root of 2 over n. And now from there, you just need to know one of these boxes. I like to just use the first one. Sine of 0 is 0, which means our n is equal to 0 here. And then you just go up by 1, n equals 1, n equals 2, n equals 3, n equals 4. With cosine, it's the opposite. 4, 3, 2, 1. So when we plug these in, what do we get? Square root of 0 over 4 is 0, so sine of 0 is 0. Square root of 1 over 2 is 1/2. Sine of 30 is 1/2. Square root of 2 over 2 is sine of 45. Square root of 3 over 2 is sine of 60. And square root of 4 over 2 is the same as 2 over 2, which is the same as 1, and that is sine of 90. Cosine, it's just all of that flipped. So 1 goes here. Square root of 3 over 2 goes here, and so on and so forth. Cosine of 0 is 1. Cosine of 30 is square root of 3 over 2. Cosine of 45 is the same as the sine of 45, square root of 2 over 2. Cosine of 60 is 1/2. And then cosine of 90 is 0. Tangent is just sine divided by cosine. 0 divided by 1 gives you 0. Tan of 0 is 0. 1/2 divided by square root of 3 over 2 is 1 over the square root of 3. When you rationalize this, this is just the square root of 3 over 3. The square root of 2 over 2 divided by the square root of 2 over 2, that's just 1. Same number divided by itself is always 1. Then we have square root of 3 over 2 divided by 1/2. 2's cancel out, and you just get square root of 3 over 1, also known as just square root of 3. And then last but not least, we have 1 divided by 0. 0 is the denominator, so we have an undefined value. And so this slide is just putting everything into perspective in terms of our famous right triangles, right? If you want to figure out cosine of 60 and sine of 60, we can look at this right triangle here. If you want to figure out cosine and sine of 45, we can look at this right triangle. And if you want to figure out cosine and sine of 30, we can look at this one. That's why right triangles are actually so important in math and in life. Our second objective for today is identifying the domain and range of sine and cosine functions. And so the domain of sine and cosine functions are all real numbers. We have no restrictions. And that's because they're sinusoidal. They keep on going on forever and ever in a loop along our x-axis. However, we do have restrictions on our domain or on our range. Our range has a lower limit and an upper limit from -1 to +1. Those are the lowest and the highest outputs that can be reached. Now, when we look at it from a unit circle perspective, we put bounds on our x coordinate. And the bounds for a unit circle is from -1 to 1. The bounds for the y coordinate, which just happens to be the range, is also -1 to 1. So the range of both the sine and cosine functions, once again, is -1 to 1. Okay. Now we're at our reference angles. Now, reference angles, I'll try and make this as simple as possible for you, but they're simply the angle that is associated with your terminal side and the closest x-axis side. And what do I mean by that? Well, let's look at our first quadrant. If we have our terminal side, we'll highlight that in yellow. And then we have our x-axis, we'll highlight that in pink. Between the yellow and the pink, we have our terminal angle. And lucky for us, in the first quadrant, the angle itself is actually equal to the reference angle. Now, they notate reference angle by apostrophe, but sometimes I usually like to use theta with a bar over it or theta with a hat over. Sometimes you'll see T with a bar over it. So these are just notations for reference angles. If we look at the second quadrant, again, terminal side is yellow, and then the closest x-axis side is over here, which means the wedge between that gives us our reference angle. Reference angles are really important because we are way more comfortable calculating the reference angles, and then from there can find out what the calculation of the original angle we're looking at is. And just to finish this up, we have x-axis closest to the terminal side, between that reference angle, and then terminal side, x-axis closest to it, terminal angle, reference angle, and we're good. So now let's practice this. Let's find the reference angle for each of the following angles. It's also important to note that all reference angles are always positive. So reference and then we deal with the negatives and the signs later on in our calculations. So what is our reference angle of 150? Well, if we were to draw this out, 150 ends up around here, which means the angle closest to our x-axis is 30 here. Yeah. So for part A, our reference angle is equal to 30 degrees. Part B, we have negative 45 is down this way. Which means our reference angle is just 45. Part C, now we're looking at it in terms of radians. 9 pi over 4, well, 8 pi over 4 is the same as 2 pi. So that's one full rotation around. And then we get another pi over 4. So we're at here, which tells us that our reference angle is pi over 4. And then last but not least, we have our part D. Let me see if I can shrink these, give some more space. So part D, we have negative 5 pi over 6, which is pi over 6 more than just pi, and it's negative, so we go down one full rotation. That gives us sorry, it's pi over 6 less than 1 pi, so it will stop right over here. And pi over 6 is about 30. Which means our reference angle is pi over 6. And we're done. Objective 4 is being able to use reference angles to evaluate our trigonometric functions. And so if we're given an angle in standard position, then we find the reference angle and then the cosine and sine of that original angle. So now let's practice this. We're going to use the reference angle and find these exact values. And we already found that the reference angle of 150, right, in this example is just 30. So we're just going to bring that over. We have our reference angle. If t equals 150, then our reference angle is 30. But we also want to look at this, and I'll teach you the acronym in a moment, with our trig functions being positive and negative in certain quadrants. But we know straight off the bat that if 150 lies in that second quadrant, this coordinate point, we'll call this P here, is going to be a negative x value and a positive y. So that tells us that our cosine of 150 is the same as negative cosine of our reference angle 30, and our sine of 150 is the same as our positive sine of 30. And we know that sine of 30 is just 1/2. Cosine of 30 is square root of 3 over 2, so we get negative square root of 3 over 2, which tells us that that's it. That's our answers, or these are our answers. Just gonna move this over a little bit, maybe shrink it. And there we have it. Now let's answer part B, where we want to find what is cosine 5 pi over 4 and our sine of 5 pi over 4. So let's find our reference angles. Five pi over 4 is a quarter more than pi. So this is 4 pi over 4. And then we have 5 pi over 4 is over here. Which means our reference angle is just pi over 4. And we're in this third quadrant here, and what do we know in the third quadrant? All of our x and y's are negative, so cosine 5 pi over 4 is the same as negative cosine of pi over 4, and cosine of 5 pi over 4 is the same as negative sine of pi over 4. Pi over 4 is the same as 45 degrees. Cosine of 45 and sine of 45 are both square root of 2 over 2. So our two results are going to be negative square root of 2 over 2. And we're done. So this is just putting everything that we learned now together, aka our unit circle of our trigonometric functions. Looks super complicated, but again, if you zoom in on that first quadrant, it's just our 30, 45, 60, 90. And then if we zoom out, these are just the reflections of these points in each of the quadrants. So all of these values are just the same, it's just they're negated in certain quadrants over others. And that actually brings us to maybe a slide I'll create on where our trig functions are positive versus negative. And so you know that we have our first, second, third, and fourth quadrants, and you figure that out by if you start in your first and you draw the letter C, then it works in that path, 1, 2, 3, 4, we're done. But there is an acronym. All students take calculus, and this acronym tells us that in our first quadrant, all trig functions are positive. In our second, only sine, as for sine related functions, so sine and cosecant are positive, everything else is negative. In our third, only tangent related functions are positive, so tangent and cotangent. And then in our fourth, only cosine related functions are positive, so cosine and secant. And there's a more formalized version of this, I believe, in our 7.4, but I'll write it in now because I think it will be helpful. And so now we're going to use our reference angles to find coordinates. Again, really using that polar coordinate conversion of x is equal to cosine of t and our y is equal to sine of t. So in our example 7, we want to find the coordinates of the point on the unit circle at this angle. Let's go ahead and create our unit circle. 7 pi over 6, well, 6 pi over 6 goes over here, and then another pi over 6 is down over here. We want to try to find that p. So what is our reference angle here? That's just pi over 6. What quadrant are we in? We're in our third quadrant, so only tan-related functions are positive. And so our sine and cosine are going to be negative, right? We have our x comma y, and again, our x comma y in polar coordinate form is just our cosine t comma sine t. And so our cosine of 7 pi over 6 is the same as negative cosine of pi over 6. And our sine of 7 pi over 6 is the same as negative sine of pi over 6. Negative sine of pi over 6 is just negative 1/2. And negative cosine of pi over 6 is negative square root of 3 over 2. Therefore, our coordinate P is equal to our negative square root of 3 over 2, comma, negative 1/2. And we're done. And so this was our last example from our section 7.3 on unit circles. The next section will be our 7.4 involving other trigonometric functions. So specifically our cosecant, our secant, and our cotangent functions. I hope this was helpful, and I'll see you guys soon. Take care.